NMR front, let's imagine that we have a molecule of this type. And we're just going to have some R groups here since they're not directly involved with this problem. But this particular compound is a sugar derivative. And I want to focus on this hydrogen right here. Let's call it H1. And then at this carbon, let's have another hydrogen, H2. And then there's a hydrogen, H3, at that position right there. And so what I want to think about is the proton NMR peak corresponding to hydrogen 1. And I'm going to tell you some coupling constant values. So the coupling constant between hydrogen 1 and hydrogen 2, let's say that's 6 hertz. And then this is kind of an interesting situation because there turns out to be a longer range coupling. If we go from H1 and we start counting through bonds, there's 1 bond, 2 bonds, 3 bonds, and then 4 bonds, and you get to H3. Normally 4 bonds away would be too far to see any coupling. But sometimes when the path between 2 nuclei passes through a pi bond, one will see a longer range 4-bond coupling. So there does turn out to be a coupling constant between hydrogen 1 and hydrogen 3, even though they're 4 bonds away from each other. As we might expect, that's not a very big coupling. So it's about, in this particular case, let's say, 1 hertz. So given this information, the coupling between H1 and H2 and between H1 and H3, can we show what the proton NMR peak for H1 would look like? Hopefully you've worked through some similar problems in the assignments. Remember, you can use this kind of splitting diagram or tree diagram to outline what would happen to H1 under the influence of H2 and H3. So give that a try, and then we'll work through the solution together. All right, so the way that you do this is you say, okay, well, here is going to be the peak for H1 in the absence of any coupling. And then we will take these couplings in turn. Let's start with the coupling to H2. There's just one member of H2, so H1 will be split into a 1 plus 1 equals 2 into a doublet because of H2. So on our diagram over here, these kind of these diagonal lines here just mean H1 gets split into this piece and it gets split into that piece. And this would be the coupling constant between 1 and 2, which in this particular case is 6 hertz. So if you kind of get into this, get some graph paper, and you can do it with each little block on your graph paper being 1 hertz. Then you can keep everything more or less to scale. Otherwise, I'm just kind of doing it freehand here. But the splitting here, we would go an equal distance this way, equal distance that way, so that this splitting now is 6 hertz. So that takes care of the interaction between H1 and H2. But now I have to factor in this splitting. And so what I need to do is I need to go to each of the wings of the original thing, and I need to split each of those according to the influence of H3. Since there's just one member of H3, it's going to split each of these lines into 2 peaks. And this value right here, that is J13, which is supposed to be 1 hertz. Again, my drawing might not be exactly to scale, but you get the idea, hopefully. And so look what happened. We started with the original peak for H1. It gets split into a doublet by hydrogen 2 with a coupling constant of 6. And then each of those lines gets split into a corresponding doublet with a coupling constant of 1. So instead of having just one line, I will have 1, 2, 3, 4 lines in the spectrum. So what I need to do to finish off this problem is to really just, here's the baseline of my NMR spectrum. And below these lines right here, I just need to draw what I would actually see for the proton NMR peak of H1. So I have to know something about what a doublet looks like. When you split a line in NMR into a doublet, the two lines of the doublet have the same intensity relative to each other. So when we split this initial line, I would have two equal-sized peaks. And then when those two equal-sized peaks were further split into two more peaks, the doublet over here and the doublet over here should have the same size. So my final spectrum, maybe I'll put it in green or something, would look like a line here and then another line here. Notice that this is a doublet, 1 to 1 in terms of the height of those peaks. And then here's the second doublet. And again, I need to have the same size doublet because what I have now is a doublet of doublets. So I could call this doublet of doublets. This analysis, this type of analysis is required anytime I have one type of hydrogen which is split differently by several other different types of hydrogen. In this case, two other types of hydrogen. H1 is split with a coupling constant of 6 by H2, and it's split with a coupling constant of 1 Hertz by H3. So I need to consider those two couplings separately and generate what I finally would expect for the overall peak associated with H1, which in this case is a doublet of doublets.